So this right here is Faraday's Law, and it looks really complicated, but I'm going to simplify it in just a second. First of all, what Faraday's Law says in words is that a changing magnetic flux will induce, i.e. like create, pop out of nowhere, an electric field and an EMF. So what is a magnetic flux? By magnetic flux, we mean this thing right here, this integral of magnetic field B dot dA, A is the area. This is the magnetic flux, and we give it a name, like a symbol. The symbol is this phi with an M. The M means magnetic, because you could have like electric flux, but this is magnetic flux. It's trying to measure how much magnetic field is getting caught or piercing an area. That's what we're doing, and you might be like, I don't know what that means. Well, here's what it means. Look, if you got an area, this circle here, imagine this is like a copper hoop. The gray part here defines the area we're talking about. The area of this hoop is being pierced by this magnetic field. These arrows here are the magnetic fields. I've got the ones piercing the hoop, shaded in blue, so you can tell which ones they are. Looks like that. So a lot of times it's drawn like this in your book. But it's like, what? That doesn't look like an arrow. Yeah, I know, but like you got to imagine. So what we do is like, hey, if it's an arrow pointing at you, we're going to draw it like a dot with some circles around it. So here's some magnetic field piercing our hoop. But what we really mean is like, this right here. So that's a flux because there's arrows getting caught, magnetic field piercing through that area. So what Faraday's Law says is if you change this magnetic flux, if this thing changes, it's not enough to have magnetic flux for Faraday's Law to give you an EMF or a field. You have to have a changing magnetic flux. So that's what this derivative here is doing. This derivative here stands guard, and it watches over this integral, this magnetic flux. And this derivative is like, hey, anybody in here changes in time, because I'm taking a derivative with respect to time, I'm making all of this stuff over here. So that's what it does. If it makes this stuff, what is this stuff over here? This is the electric field, and it's also the EMF. You might be like, I don't care about the electric field. Yeah, most people don't. When you're doing Faraday's Law, a lot of times you don't care about the electric field. What you care about is that electric field times length has units of volts. So you're like, ooh, I do be caring about the volts because, Ohm's law says if you got volts, you divide that by your resistance, and that gives you your current. So this has units of volts, but I have to warn you, this is technically not a voltage. It's not a difference in electric potential because it's not getting created. This electric field is not getting created by a net charge. It's getting created by a change in magnetic flux. This is what blew people's mind in Faraday's time. He was like, hey, Faraday was like, look, I can make an electric field. And people were like, okay, where's the net charge creating it? And he's like, I don't have a net charge. I just changed my magnetic flux, and this E field popped into the ether like a magic trick. And they were like, what? How can you do that? Well, because this electric field is not getting created by a net charge, don't call it a voltage. Your professor will cringe if you say that. It has units of volts. So this whole thing here in this box, it looks like volts, it tastes like volts, it smells like volts. You can plug it anywhere that volts goes in all of your formulas and it works just fine, but it's not technically a voltage. So we give it a different name. In the textbooks, you can think about it as a voltage, but in the textbooks, they got to be proper. They call it an EMF, which is ironic because, Professor B getting all uptight about me calling it a voltage. Guess what EMF stands for? Electromotive force. This sucker's not a force. It doesn't have units of newtons. It's just a bad name. It's kind of a historical name, but it's got units of volts. So I'd rather call it voltage than an EMF, but whatever. Everybody calls it EMF, but it's a volts. It's a number of volts. That's what we care about. So really, you don't do any of this integral here. You just find this side and you say that's equal to my volts, my EMF. And we care about that because that gets current flowing. So I just wrote this whole thing right here. The EMF is usually what you want to find. I set it equal to negative d dt. You might be like, whoa, but you wrote this different. Yeah, because without loss of generality, you can always write a dot product as the magnitude of the one vector times the magnitude of the other vector times cosine of the angle in between those two vectors. So this is usually how you're going to deal with it. You don't really want to deal with the dot product typically. You typically want to deal with it like this. This is the easier version than the top one I just showed you of Faraday's Law, but it's still pretty gnarly. There's an integral here. And you might be like, wait, I don't know what this angle means. What do you even mean by that? So this angle is the angle between the magnetic field and the area. So in this case I just showed you right here, you might be like, well, I know which way the magnetic field goes. It goes straight up. So I know that the magnetic field is going straight up. Which way is the area going? We define the direction of the area as this direction perpendicular to this face, this surface created by the area created by this hoop. And you could write it as dA. That's also the direction of dA or A. So in this case, B and dA go both the same way. And so the angle between them is 0, and that means cosine of 0 would be 1. This is the way you want to orient it. If you want to get magnetic flux, you want to orient it like this. Like if you go jellyfishing, you know, you're SpongeBob jellyfishing, this is how you want to hold your net. Look at all that flux piercing your hoop. If this was like a net, look at all the jellyfish flying through your hoop. There's a lot of flux. You want that B pointing in the same direction as your DA. You could, you know, you don't want to do this. You don't want to be a Squidward over here pulling one of these jams. It's like, oh, dude, you're not catching nothing now. Like it looks like you are, but all these field lines are just glancing the top of your net. None of them are actually piercing through your net. You can imagine intermediate angles where you have like something like this. All right, at least you'd be catching something. You know, this isn't perfect, but at least you're catching something. So in this case, your area vector would point this ways right here, you know, perpendicular to the face of your area. That's the A or the DA, whichever one. This way is B. So these are external magnetic fields getting created by something here. This is the direction of the magnetic field, and that angle is this right here. This here would be your angle that you want to find. So when I write BA cosine of theta, I'm talking about this here. That's what that cosine of theta is. You might be like, why is it that theta? Well, look, the only part of this magnetic field that matters, that creates flux, is the one going through the hoop. So look, this B field here, the only part of it that matters is the one going this ways. So that's why I want to do cosine theta. Look, this piece here is the adjacent part of that hypotenuse. So I want to take cosine of theta to get this piece. This piece doesn't give me any flux. It's just this piece. That's why we have that cosine theta right there. So you get this formula here. It's a little better for Faraday's law. And you're like, okay, well, how do I actually do this? If I wanted to actually go to the lab and change the magnetic flux, what would I do? Well, you got 3 choices because there's 3 things in here. There's B field, there's area, there's theta. So you can either change, you know, DDT, change in time the magnetic field. So maybe this magnetic field gets more and more intense, you know, gets stronger or weaker. Or you change the area. Maybe your area was small at first. You had a small circle. And then somehow can, like, you know, the metal can slip past each other and you get a bigger area. You're catching more flux. So that's another way to change the magnetic flux. Or you change the angle. So maybe you have this rectangle and you just rotate it in a magnetic field so that that angle you're creating here is changing in time. That's the third way to do it. Those are the only ways to change your magnetic flux. And if you do that, you'll get volts, which means a current will start to flow. Okay, so this is still honestly more complicated than what you'll usually have to do. So you can simplify this even. You can simplify this even more, and you can say, well, shoot, if my magnetic field is uniform. What does uniform mean? It means the same through space. So the magnetic field doesn't change when you go that way, and it doesn't change when you go this way. So in space, the B field is uniform. If that's the case, this integral only cares about space, like it's integral over space. So if your B doesn't depend on space, it gets to get smuggled out of your integral. Even if it's time dependent, it could just come out of this integral. So that's cool. And if your theta doesn't depend on space, like if your angle is always in the same direction, you know, for this example we had up here, if our angle is always, like even though there's an angle, it's always the same angle all the way through, it's uniform, you can smuggle that out of your integral, and that can just come out front. And what you'd be left with is, think about it, you'd have negative ddt. We smuggled B out, we smuggled cosine theta out, you'd just be ended up with integral dA, but the integral dA is just A. So we take this, we just call that A. This is B. That's cosine theta. We just end up with this formula right here, which is the simpler version of Faraday's law. If the magnetic field is uniform in space, you know, same throughout space, then you can use this easier version right here, which is kind of nice. When wouldn't you be able to do that? Well, if B is not uniform. What would that even look like? It would look like this. Look, here's a magnetic field that's not uniform in space. Look, if I move to the right, my magnetic field's getting more and more intense. I'm representing that with longer line arrows. The other way you could represent it, from this direction, you can't really tell. You're like, dude, I can't tell if it's getting more intense. So a lot of times what we do, you know, on a page that's not 3D, first of all, we draw these with a little circle around them because, like, if the arrow's coming at you, you see the dot, these would be arrows coming at you. To draw this getting more intense, we often just draw more of these. So this would be a magnetic field that's more intense here on the left than it is on the right. It'd be a non-uniform magnetic field, or the way I had it drawn earlier, more intense on the right means there's more of these arrows coming at you on the right. So that'd be non-uniform. And if that magnetic field is non-uniform, well, then you just got to do this integral. You just have to actually do this integral. The B cannot sneak out the back door because this dA is always watching. This dA is like, hey, anybody in here depend on space, I'm going to integrate you. And you have to leave the stuff in there. But if B is uniform, You don't have to do that. So let's try some examples. How do you do this? Well, one thing might be bothering you. You might be like, what the heck is this negative doing out here? Okay, there's a whole story behind that. I'll get to that in a minute. I don't want to bore you though. That's Lenz's law. We'll get to that. Let's just first do a couple problems. Let's kick the tires. So there's three things you can do. Change the magnetic field, change the area, change the angle. First, we'll do some examples where we change the magnetic field. So here's an example. We got a magnetic field piercing this rectangular hoop. So we got a flux. Look, we got a flux here. So I can use the easy version because this magnetic field is uniform through space. It doesn't vary vertically or horizontally. It's the same value throughout space. So we get to use this easier version of Faraday's law. And the way you do it is you just find what your B is, throw your B into there. Find what your A is, but that's just height times width. You know how to find area. Find your angle, but the surface area here, the area points straight out, the area vector. B points straight out, so it's cosine of 0, and cosine of 0 is 1. So that's good. But you always got this derivative out here lurking. This derivative looks inside, it's like, hey, anybody here change in time? And they're like, no, sir, no, ma'am. Okay, well, shoot, I annihilate all you. I take a derivative of a constant, I get 0. So in this case, even though you had a flux, you get no EMF, no volts for you. No current's going to start flowing here because there was no change in that flux. It's not enough to have a flux. You have to have a changing flux. So that one's kind of easy. You might get tricked on a test. You might be like, hey, real complicated setup, but if nothing's changing in time, it all gets annihilated. And so no EMF. All right, what if you do have something changing in time? Here's a magnetic field changing in time. We got some constant times c squared. So it's getting more and more intense. As time increases, I get more and more magnetic field. But I don't have to do my integral version because this B field gets uniformly greater. Like it gets more on the right and on the left at the same time and in the middle. So it's not like a function of space. So I get to do my easier version of Faraday's law. And what I do is just plug in my value. I plug in what my B is, constant times t squared. That goes there. That's why I have this. You know how to find area, height times width. The angle's still nice, and cosine 0 just gives me 1. All right, so I got all that. My derivative's now like, hey, C, do you depend on time? Nope. Okay, you can get out of here. HW, depend on time? Nope. You can sneak out the back door. All that's left in there is the t squared, but the derivative of t squared is just 2t. So the 2 comes out. I get 2HW. CT is the EMF. The number of volts would be this. So if I wanted the current that flows, I could take the number of volts, 2HW CT, and then divide by, if I knew the resistance of this circuit, I could just divide by the resistance. But which way does this current flow? That's the question. That's what this negative's here for. And I'll be honest, almost everyone that does these problems just finds the magnitude of the EMF. They just make it positive. And then they have a different way to figure out which way this current flows. Does it flow clockwise or does it flow counterclockwise? So there's a rule to figure this out. That's what that Lenz's law was up above. So how do you figure out which way the current's going to flow? Lenz's law says that wires hate a changing flux. They want to keep their flux. Whatever it was, they want to keep it. So this wire here had a small amount of flux. Then you increased it, and this wire was like, oh, dang, heck no. So you increased the flux. You get all this new field coming out of here. So this wire's like, okay, I'm going to oppose you. I'm going to fight the change. So it starts creating its own magnetic flux that fights all this extra, tries to delete them by making magnetic field go the other way. That's why I have these X's here. These X's are representing the induced magnetic field. What is inducing the magnetic field? A current is. So a current is going to induce a magnetic field. This is not the external magnetic field. Like this blue is an external magnetic field created by some other, magnet. But a current's going to flow in here. And the way you figure out which way that current flows is you figure out which way would you point a magnetic field to fight the change. So I'm going to fight this increase by having magnetic field into the page. And now we use the right-hand rule. So this right-hand rule says, if you got a magnetic field into the page in the direction of your thumb, your fingers will swirl in the direction of the current needed to create that magnetic field. So try it right now. Stick your thumb sort of in the direction of your screen, and your fingers are going to be swirling this way. That's why I draw these arrows this way. That's the direction of the induced current. So what happens here is you got a hoop minding its own business. There's no current. You boost the flux by increasing it. And this wire is going to be like, no way, I don't like that. So it creates a current. The current that flows is from that induced EMF, and it flows this way in order to fight all these extra magnetic fields. It's not going to win. It's always going to lose, but hey, it tries hard. It tries to fight this flux. It doesn't actually succeed in doing it. It can't cancel all of it typically. Okay, what's the other example? Well, let's say you decrease the flux. So if you decrease the flux, if you had a hoop that was this big, and you go back to what it was, you might think, oh, it's going to be happy now. No, this hoop has no memory. It's always fighting what you did. Now it's going to be like, oh, I liked this large amount of flux. I want to keep it. It's always trying to keep whatever it just had. you're like, whoa, you got rid of these? No, no, no. I want to keep these. You just got rid of them. I'm going to try to put them back. It fights the decrease by trying to put them back. That's why I drew these induced magnetic fields going in the same direction as the external magnetic field. So which way should the current flow to do that? Well, take your thumb, put your thumb in the direction of this out of the page, and you'll realize your current should flow that way in order to do it. So I got it written down here. You can read it if you want. I'll share this document in the comments. But, if the magnetic flux increases, put your thumb opposite the external magnetic field. Your fingers curl in the direction of the induced current. If your magnetic flux decreases, place your thumb in the same direction as the external magnetic field, and your fingers curl in the direction of the induced current. So let's try it out. What did we find here? So the first question you ask is, was flux increasing or decreasing? Well, look, as time increases, B is increasing. So we're getting more and more magnetic flux in here. And our hoop's going to be like, oh, hell no, I don't want that. I want what I had, so I'm going to try to get rid of you. So it creates an induced magnetic field into, put your thumb into, and you realize the current's going to be flowing in this clockwise direction. That's why you typically don't care about that sign. You just find the magnitude of the EMF. You figure out the direction of the induced current separately. And again, the current would be whatever that EMF was, 2HWCT over whatever the resistance of the circuit was. Okay, so that was an example of Faraday's law. Let's do another one. What if you got a circle and the magnetic flux is decreasing this time? Look, I'm subtracting as time increases. So I'm subtracting flux that's coming out of the page. So, same thing. B is uniform. So if B is uniform, we get to use the easy version of Faraday's law. We're going to take this B, whatever it is, and we're going to put it in for B. That's why I have it written here. We take the area. You know how to find the area of the circle, pi r squared. And the angle's all nice. Area of the direction of the area and the B field point the same way. So cosine of 0 is just 1. All right, and then your derivative's sitting here waiting. It's like, hey, I'm going to operate on you. You depend on time. Pi, no, I don't. Sneak out front. R squared, no, I don't. Sneak out front. That's why they go here. So it's going to take a derivative of this here, but B is a constant. We're assuming B and C are constants. So B is a constant. You get annihilated. So I get the derivative of negative CT squared. That'd just be negative of 2CT, so the negative got canceled here. But it doesn't matter because we're going to figure out the direction of the current separately. So if I wanted the current would be whatever the EMF is over R. And again, be careful. I'll use little r. Little r for resistance. Little r, not capital R, like radius. This would be the resistance of the circuit. And you'd figure out which way it flows using Lenz's law. You'd be like, all right, does my flux increase or decrease? This time it decreases. You're like deleting these. It's like, oh no. So this wire's like, oh no, I'm losing my flux. I want it back. I want to keep the same amount I had. So it tries to put it back. So now you stick your thumb in the same direction as the external magnetic field. This is the induced red magnetic field, and your fingers will curl this way. This is the induced direction of the current. So that was an example where flux decreased. What if the angle is important? So next time we've got an angle going through here. That's okay. Magnetic flux is still uniform. So we get to, do the easy version of Faraday's law. We do this version right here. We take our B field, whatever it is, we take CT squared, and we take this and put it into B. So I take CT squared. Area is still pi r squared. But this time we have a cosine theta that matters. We need cosine theta because we need only the part of B that goes through that hoop. So I got that. Everyone can sneak out. All of y'all can get smuggled past the derivative except for t squared. The t squared is going to have to take a derivative. So I get 2t out of that, and so I get my EMF as this. And again, you can do Lenz's law. Does flux increase or decrease? It increases. We're like increasing how much B goes through here. And so our hoop's like, oh, heck no. I'm going to try to get rid of you. It can't create an angled one, but it can create a down one. I'm trying to fight you. Put your thumb down, and you realize, okay, current will be flowing around that way. So that's another example. How does this get harder? Okay, what if you had a magnetic field that actually was non-uniform? That is to say, if you head out in the rightward direction, what if you do get more and more magnetic field that way? This is like this example right here. Non-uniform magnetic field. Now you have to do the integral. So we're going to have to integrate. We can't smuggle B out of this integral because this integral dA is like, hey, anybody in here depend on space? And the B is like, yeah, I do. Look, I depend on X. So you take whatever, you take your B, you throw it in here. That's why I have CX t squared. Integral dA. At least our angle between area and B is still just cosine of 0, so it's 1. So let's see, can anyone get smuggled out of the integral? C can, that's a constant, doesn't depend on space. Even t squared can get smuggled out. You're like, what? But that's a variable. Yeah, but it's not a variable of area. Like it's not a variable of X or Y, space. It can't get smuggled out of the derivative, but it can get out of the integral. And so you get this integral x dA. You might be like, what's dA? Well, it's a dx times a dy. So a little bit of height times a little bit of width gives you a little bit of area, an infinitesimal area. You might be like, but that's a double integral. How do I do that? Okay, that's okay. What you do is you say, hey, I got nested integrals. I got my first integral here. Whatever comes out of this integral is going to be the thing that my y integral is going to integrate. So this is kind of nested in here, and you can do them in either order, but I'm going to do the x one first. So my x integral happens first, and it's like, hey, what's the integral of x? Well, that's easy. It's x squared over 2. Between 0 and w just gives me w squared over 2. And now my y integral is like my turn. I'm going to integrate whatever u are. So the y integral looks in here is like, hey, anybody depend on y? And w is like, no, I don't depend on y. I'm the same w, as high as you go, same width. So these are all constants. It doesn't matter. You can take them out of the integral. Integral of dy is just y. From 0 to h just gives you an h. You get your w squared over 2. You still had your ct squared weight now here, and now your derivative acts. Your derivative is like, hey, anybody depend on time? Well, the only thing that depends on time is t squared. So you get a 2. That'll cancel with this 2, and you end up getting this as your EMF. You don't really care about the sign because we're going to figure out that separately. You ask yourself, does the flux increase or decrease? Well, it's increasing. As time increases, we're going to get more and more flux. So we'd be adding all this flux in here, and our wire's like, no. I wanted to keep how much flux I had, so I'm going to try to fight you with my own induced magnetic field. So we take our thumb, point it into the page, and your fingers are going to be swirling clockwise. This is going to be the direction of the induced current created by this EMF volts. So that was that example. These might look hard, but you got to be ready for these. Like in engineering physics class or an AP Physics C, you're going to meet these. Here's a harder version of the one I just showed you. This time, we actually get to discover what's creating the magnetic field. I told you it was an external source. So here's a wire with a current. Currents create magnetic field, and this current is AT squared. So it's getting bigger over time. And we can figure out which way the direction of the field points from this wire. Use your own right hand rule, stick your thumb in the direction of this current, and your fingers will curl into the page up here. That's why I got X's. They're going into the page. If you see an X, that's an arrow going into the page. What is all of this? What is mu naught I over 2 pi r? Well, that's the formula for the magnetic field from an infinite straight wire. This comes up so often, you should kind of just memorize it. You can get it from Ampere's law, mu naught I over 2 pi r. So you take your I, whatever the I is creating that B, and we put it in there. That's why I have mu naught A t squared. Divided by 2 pi. Well, what is r? R is how far you are from the wire. So r is this y direction. So I'm just going to call it y. So this is my magnetic field. And it gets weaker as I go farther away. Like the bigger y gets, the weaker B gets. So I have to do the integral version of this Faraday's law because this area integral is like, hey, any of y'all depend on space? And the B is like, yeah, I do. I depend on y. So that's okay. Take this, put it in for B. That's your B. I get dx dy. That's what my A is. My angle's still nice. Cosine 0. This gives me 1. And then, sorry, let's clean this up. Who can sneak out of the integral? Anybody that doesn't depend on x or y. So that's everything, including the t squared, except for the 1 over the y. That's the only thing that has to stay. Everything else gets smuggled out. In fact, everything else except the t squared gets smuggled out all the way past the derivative. It's only the t squared that can't move past that derivative because the derivative's checking for things that depend on time. Okay, so how do you do this? You do your integral first. We'll do the y integral. So I got 1 over y, dy. That's going to be log of y. So what I'm going to get is like log of, d plus h. You might be like, why is my limit d plus h? Because look, the farthest I go is d plus h. And the closest I am in this hoop, we're worried about the area here. Remember, it's this area. The furthest that area is in y is d plus h. The closest it is d. So I go from d to d plus h. And so when I do that, evaluate that, I get log of the top limit minus log of the bottom limit. But the difference in logs is just the log of the ratio. So I can write this as this here. And now this comes down here. And now my x integral takes over. My x integral is like my turn. I'm going to integrate anything that depends on x. And the x integral is like, oh man, there's nothing that depends on x here. So I can actually smuggle this whole log out of this integral. Like this d doesn't depend on x. This h doesn't depend on x. Nothing there is x dependent. So integral of dx is just x from 0 to w, just gives you a w. So you end up with this log times the w, all the stuff I smuggled out. And then the only thing that depends on time is t squared. So you get the 2t from that. So I get this right here. And then again, don't care about the sign because we're going to figure that out separately. Does our flux increase or decrease here? Since the current's increasing, the magnetic field increases. We're getting more and more field into the page. And this copper hoop's going to be like, no. I don't want you. I'm going to try to delete you by creating my own, I'm trying to cancel you by making my own magnetic field that comes out of the page. So put your thumb in the direction of this red induced magnetic field, and you'll realize your induced current is going to be flowing that way. So that's about as hard as you get for the changing magnetic field examples. So you could change magnetic field. You could also change the area. What would that look like? So let's say our magnetic field just stays the same forever. And it's uniform. So it's uniform and it never even changes in time. It's just a constant, B naught. So it's uniform. So we're definitely not going to have to do an integral here. We get to use the easy version of Faraday's law. So we take our B, whatever it is, we plug it into there. A is going to be pi r squared for a circle. You got to be careful. R is a function of time now. Our R is increasing in time, 2 times t. So that's okay. We take that, we put that in here, pi times r squared. The r squared goes for r, but pi gets smuggled out, b gets smuggled out. Neither of these depend on time. So they get to get smuggled out the back door for this derivative. 2t squared is going to be 4 times t squared. The derivative of that is just 8t times b naught times pi. Which way does the current flow? Well, did flux increase or decrease here? Flux increased. We're gaining all these extra arrows out of the page. So our wire is going to be like, hey, I want to get rid of you. So I'm going to make my own induced field that goes into the page. Stick your thumb into the page and you realize your induced current would go that way. So that was one example. Here's another example you see a lot. If you got a rod sliding on a hoop right here, this this rectangular hoop, and a rod slides on it and there's an external magnetic field. So in other words, this rod was like here, and then it's going to be over here at some later point, and then it's like over here, and this keeps going on forever. You're increasing your area. This is an example of increasing area. So how do we do this? Well, same old Faraday's law, and the B field's uniform. B is the same everywhere to the right and vertically, so we can use the easy version without the integral. So we take our B, we take that, plug it in there, and that's a constant. We can smuggle it out the back door, that derivative. We take our area, that's going to be length times width. You might be like, I don't know the width. That's okay, just write it as length times width. The angle's still nice. Angle comes out of the page. Oh, well, let's define the area as into. We're going to get rid of the sign anyway. It honestly doesn't really matter. But anyways, the angle gives you a cosine of either 0 or 180. You either get 1 or -1 here, but we don't care because we're going to get rid of the sign in a minute. All right, so this derivative's like, hey, who in here is changing in time? And the length is like, not me. So, okay, you can sneak out the back door. How about W? Yeah, W changes. Look, the width of this rectangle gets bigger and bigger in time. And you might be like, well, I don't know what the derivative of W is, but you do. If the speed of this rod is V, V is how fast you're changing the width in time. If this is moving to the right at 3 meters a second, you're gaining 3 meters of width a second. So dW dt is V. So you just get BLV is the EMF. This is important. This result comes up so often, you should just memorize it. But I like memorizing like this. I rearrange the letters. I call it LVB because this looks like Las Vegas Boulevard. And if you've been to Las Vegas Boulevard, there's a lot of volts on Las Vegas Boulevard. There's lots of lights and stuff. So LVB equals the EMF from a rod moving through a field. So that's cool. You can get that. If you knew the resistance, take LVB, the volts, over R. That gives you the current. Which way would the current flow? Well, we're increasing flux. Our flux is increasing. We're getting, this rod will be over here. And it's like, dang, now our area is including all of these as well. So our hoop's going to be like, no. I'm going to get rid of you. I'm going to try to cancel you by making a field the other way. So since we increased flux, I'm going to put my thumb in this direction out of the page, and I get that my current's going to be flowing in this direction. It'll be this big. And if I got a current flowing in a magnetic field, I'm going to have a magnetic force. The force is ILB, Philb. And so I take my I, this is my I put it right there. I take my length, well, this was my length of the rod. I put it right there. I take my magnetic field. I multiply that all out, and I get L squared V, B squared over R. That's the magnetic force. Which way does it point? It points backward. Magnetic force is a hater force. It's going to oppose whatever you do. You try to pull a rod to the right, magnetic force to the left. So you might be like, well, what if I push the rod to the left then? What if I get the rod going this way? Well, now, because flux decreases, everything switches, and your magnetic force this time is going to be to the right. It's like, no, I'm going to oppose whatever you do. It's like, damn, you change the flux, magnetic force is going to oppose you. So that's a hater force, always against what you do. So that's a common version, LVB. So it comes up a lot. In fact, you can think of complicated versions here. This might look overly complicated, but I swear you're going to have to do this. If you're in an engineering class or AP, got to know how to do this. If the rod slides with an initial speed V naught, and there's no friction between the rod and the rails, what's the velocity as a function of time? So first of all, this is going to slow down. It's going to slow down because remember, this magnetic force is a hater force opposing you. So it's going to slow you down. So what is the velocity as a function of time? Well, you got to do Newton's second law. You do A is net force over m, and we're writing A as dv dt because we want a differential equation. What's my force? We just found that in the previous problem. The force is L squared V B naught squared over R with a negative. The negative is important. It's saying it's opposite direction of the V. So that's what the force goes, opposite direction of the V. I divide by M. I can like combine that stuff together. At this point, I have to do the separate, integrate, celebrate. I got my V's and my T's. Those are my only variables. So I got to separate the V's from the T's. First step, separate. So I put my V over here. I divide by V. I move my T over to there. I get this over here. So I've separated. Now I integrate, step 2. So I integrate both sides. Integral of dV over V, that's just log V. Between V naught and V would be log of V minus log of V naught. I integrate this side, and this integral is like, hey, anybody in here depend on time? And this L is like, no ma'am. B is like, no ma'am, no ma'am, no ma'am. I got no time dependence. So these can all wait out front, and I get integral of dt. Well, that's just t. Between 0 and t, that just gives me t. So I get this right here, and I could write the difference of logs as the log of a ratio. How do I solve this for v? I'm trying to solve for v. This here is my v that I'm solving for. We'll take e to the both sides. E cancels log. I get v naught over v equals e to this mess. So I just multiply by v naught, and I get this right here. So this is my velocity as a function of time. Notice it's v times e to the negative, so it's going to look like this. As time increases, I start with some speed, and it dies off like an exponential in time. So that's what that looks like. Okay, that's honestly, this is the easy version of this problem. The harder version's down here, and you need to know how to do this one too. Like, this is expected that you know how to do this. Let's say I took the rod, and this time I let it fall in gravity. So this time there's a force of gravity this way. This is like downward. So I got my magnetic force. My magnetic force, the Hader force, is going to be pointing up. It's like, hey, I don't want you to change my flux. So these two are opposing each other. So it's the same situation. Let's say we wanted to find the velocity as a function of time here. We do Newton's second law, accelerations, force per mass. So I have mg down. I'm going to call this direction positive, because if you call the direction of motion positive, it just makes it easier. So mg is down minus, I got this magnetic force here over m. So again, I have to separate, integrate, celebrate here. So v and t are my variables. So you might try to separate this mg from all of these, but you can't do. You got to treat this like a family. This family moves together. So I take this whole thing and I divide over here. So I'd have dv over this whole mess. And then I move dt to the other side, get dt over m. All right, they're separated now. I integrate. Now, you have some, you could divide by m's if you want, but like this whole something minus something's got to move over here. You're never going to be able to separate it. And now I can integrate both sides. This time you're like, dang, this integral's hard. dv over all this mess, I got my v here. What do? Well, you use substitution. So call this whole bottom thing u. So I'm calling that whole thing u. du that would then be, it annihilates that. I get L squared, B naught squared over R times dV. Solve for my dV, I'd get dV as this negative mess times du. So what I'd get is that, up here I'd have R over L squared, B squared, negative. This would be du if I subbed in for dV. And then all this down here would just be u. So I'd have integral du over u. But integral du over u is just log. So I do the same thing, log of the, difference of logs, but I could write that as log of the ratio. Log of the ratio. And be careful, the zero limit here. The zero limit doesn't give you 0. You plug that zero limit in, and you get mg. It's not 0, so be careful. You get a difference of logs, and you get the log of the ratio. And then over here, it's easy. This integral's easy. Integral dt is just t over m. So you get this whole mess here. Multiply both sides. You divide both sides by that. You get this here. Take e to the both sides. Log gets canceled. And then it's just a bunch of algebra that I don't want to bore you with. You solve for this v. This is what you're trying to solve for. This v is a function of time. So you solve for that v, and you finally get this over here. What does this look like? Well, if you graph this time we dropped it. It started at rest, and it looks like that. And it gets to some terminal velocity. And you can find that by just being like, well, what if I plugged in t equals infinity? I'll wait a long time. E to the negative infinity is 0. So this here would be your terminal velocity. Eventually, you'd get to some terminal velocity where the magnetic force upward and the gravitational force downward would just cancel, and it would just move at that speed right there. Okay, that's about as hard of a problem as you can get where the area changes. There's only one more problem I want to show you. What if the angle changed? How would you even do this? Well, you take like a rectangle, you just start rotating it in a magnetic field so that right here it's catching a lot of flux, and now it's in this orientation, it's catching no flux. And it just keeps rotating, changing its angle. This is actually how most power plants work. It's actually easier to do this. You burn something, that spins something, and you get a lot of volts out because you got some magnetic field here, and you're using Faraday's law. But look at this magnetic field uniform. Doesn't depend on space. So we could use the easy version of Faraday's law. I take that. I take whatever my magnetic field is, B naught. I put it in there. That's why I got this. Area, height times width, easy. This time cosine theta is not our friend. This time cosine theta is the complicated part. The area, this angle between the area vector and B keeps changing. So how do we write this? Well, if you remember, omega, the angular rate of spin, angular velocity is d theta dt, or you could just think about it like, let's say you're spinning at a constant rate. It's how much theta you go through per time. So if we wanted how much theta you go through in a certain amount of time, multiply, you get omega times delta t. And let's just say we started at theta equals 0, and let's say time started at 0. So we just write theta is omega t. So I'm going to take this. I'm going to put it in for theta. I'm going to call that omega t. So I get this whole thing, and now we got our derivative, checking everyone out like, hey, you depend on time? No, sir. You can sneak out the back door. H and W sneak out the back door. This is the only thing that depends on time. So we take a derivative of this cosine omega t, but the derivative of cosine is sine. But we got to do the chain rule here. In fact, it's negative sign. That's why the negative got canceled, but we don't care about the negative anyway. You got to take a chain rule. So derivative of cosine is sine, but then you got to take a derivative of the inside with respect to time. That gives you an omega out here. So you get this right here. This is going to be our EMF, how many volts we get. And if you notice, it depends on omega. Like the faster you spin this thing, the more volts you're going to get. And it's going to be varying in time. So this EMF, which if divided by resistance gives you the current, is going to look like sine. So it looks like this because our resistance is just a constant, So whatever EMF looks like functionally is what I looks like. So it looks like a sine, but look at this was our flux. BA cosine theta is our flux. That depends on cosine. So that would sort of look like this. And you'd have this alternating current. We're rotating this wire in this magnetic field gives you an alternating current, and you can find what it is using Faraday's law. Okay, to recap. The way you use Faraday's law, this is the full-blown version. It says if you have a changing magnetic flux, you're going to get an electric field and an EMF. If your magnetic field depends on space, if it's different to the right than it is to the left or up or down, you got to leave that B in there and do this integral. But if it's not, then you could just use this easy version down here to find your EMF. And there's only 3 ways you could change that EMF or change that flux. You can change the B, change the A, or change the theta. In fact, you can write an even easier version of this. If you just wanted the average EMF, you could do delta BA cosine theta over delta T. This would be like poor man's derivative right here. This would give you an average EMF, but if you wanted the exact EMF as a function of time, you could take one derivative. To get your volts, once you have your volts, plug that in to any formula where volts applies, and you can find some other quantity.